Okay, so good afternoon everyone, and we're going to talk about the one-to-one, onto, and invertible functions today. So first we're going to proceed with the one-to-one function. So it is said to be that the function is one-to-one if function from A to B, wherein all elements in A has or have a distinct elements or distinct images rather. So that is the one-to-one. Or this can be read as f is one-to-one if f of A is equal to f of the image of A, or it implies that A is equal to the image of A. That's it. Now, the examples will follow after I discuss this one. So, we have this one, the onto function. Let's proceed with this definition. F maps A onto B if every element, or for every B, element of B, there exists a element of A such that f of A is equal to B. Okay, as we're going to look backward, no? The image of B is at A. That is onto function. Okay, so let's proceed with the invertible functions. A function f from A to B is said to be invertible, inverse, if its inverse relation f raised to the power of -1 or inverse function is a function from B to A. So equivalently, if function from A to B is invertible if there exists a function f of -1 or f raised to the power of -1 or the inverse function from B to A. We can simply state this one like this. We have function from A to B will be equal to function from B to A. The inverse of this should be still a function. That is one of the things that we're going to think about first. So, call the inverse of f. This is called as the inverse of f such that then f composite the inverse function is equal to 1 sub A. Simply, we discussed the identity function already. And the composite of the inverse function f, or f raised to the power of -1 composite f is equal to 1b. That's it. Or that is all about the invertible function. Now, we're going to remember that a function f from A to B is invertible. This can be invertible if and only if is both, or f is both one-to-one and onto function. So we have here an example. Consider f sub 1 from A to B, function sub 1 from A to B, function sub 2 from B to C, function sub 3 from C to D, and function sub 4 from D to E. It is being defined by this figure. So first we have A, B, C, 1, 2, 3, 4, R, S, T, U, V, W, X, Y, and Z. We have here A, B, C, D, and E. So now, we're going to determine the following. First one is that those functions that can be a one-to-one functions, onto and one-to-one but not onto, and then onto but not one-to-one, and we have invertible function. But before that, of course, note that invertible functions function, or the function is invertible if and only if the function is one-to-one and onto. That's it. So first, we're going to determine the following. What is one-to-one? So we're going to look at the figure. So we have here A, B, and C. It is connected to this. So note that A, B, all elements in A has a distinct image in B, or the image of A is in B. So this is under the function sub 1. So since this figure is something like this, then therefore we can say that function sub 1 is a one-to-one function. How about onto? Function sub 1 is not onto function because there is 3 which has no distinct image to B. So meaning to say it's not an onto function, but it is just only a one-to-one but not onto function. Okay, it is neither a or an invertible function. So that's it. So next we're going to proceed with f sub 2 or the function sub 2. We have here 1, 2, 3, 4, R, S, T, and U. Now look, we have 1 and it is connected to distinct image or distinct pair. So therefore, this figure or function is a one-to-one function because all elements in here have the distinct image. So now, again, let's have a look another round. So note that an onto function, this is an onto function rather because every element in C has a distinct image as we're going to look back. No? So R, we have 1, S, we have 4, U, we have 3, and T, we have 2. So that is, or this function is considered now as onto function. Okay. How about this one? It is neither one-to-one, onto but not, and of course, the definition states that if and only if the function is an onto and one-to-one, so we can simply say that the function is, or given function is an invertible function. So this is under the f sub 2. So another one, we have from C to D, which is a function under f of 3 or function 3. So you have R, S, T, U. Note, if we're going to look at it, R and U has an equal image. So therefore, it is not a one-to-one function. But all elements in D has a distinct elements image. So therefore, we can simply say that it is an onto function which is under the f of 3. And now, it is not one-to-one, but it is onto but not one-to-one. So therefore, this function belongs here. So another one, it is not, or this function or f of 3 or f sub 3 rather, is not an invertible function because it is not one-to-one. Next, let's proceed with this. V, Z, W, and Z. Note that the f of V is equal to Z and f of W is equal to Z. They are equal, so therefore it's not a function, it is not a one-to-one function nor onto function. So that is how we're going to determine the one-to-one function, onto function, one-to-one but not onto but not one-to-one function, and we have here invertible function. The only thing or the only function which is invertible is under the f of 2 because the f of 2 is one-to-one and onto function. Okay, so we have here an example, another one. Consider functions f from a to b and g from b to c. We have to prove that f and g, or if f and g are one-to-one, then the composition function is one-to-one or function compose or f composite g. So we have the proof, no? Proof. So suppose g of f or function composite g of x is equal to g of f of y. Now, this will be equal to, note that, or then we're going to write then, g of f of x is equal, this will be equal to this, right? then this will be equal to g of f of 1. Okay. Then, so, since they are equal, so we have, hence, f of x is equal to f of y. Since g is 1 to 1. And we have this one. So furthermore, we have x and y is now equal because we have, since f is 1 to 1. Why is it 1 to 1? Because it is given that f and g are 1 to 1 function. So, then therefore we have, accordingly, g of f, or f composite g of x, f composite g of y is, or this one, or is a 1 to 1. So we're going to write g of f is 1 to 1. This is the end of the proof. To consider the functions f from a to b and from g from b to c, prove that if f and g are onto functions, then g of f is an onto function. So to prove, we have proof. So we're going to let C be any arbitrary element of C. Now, we're going to look at the problem. So since G is onto function, then there exists B as the element of B, such that G of B is equal to the element in C. Okay. Next, let's proceed with F. Since F is onto function, they are onto function, then there exists a function A element of A such that G of A is equal to B, or the element of B, since they are onto. So of course, then we have G of F of A is equal to G of F of A. That is equal to G of B, which is also equal to the element C. So therefore, accordingly, G of F, or composition of G and F, is an onto function. Okay, that's all. Okay, so we have the A function f from A to B is invertible if and only if f, or the function, is bijective. When we say bijective, it should be 1 to 1 and onto functions. So we can simply determine that the function is invertible if and only if it is bijective, or 1 to 1 and onto function first. So suppose this is a problem. What are we going to do? We have, suppose Suppose F is both um, 1-to-1 and onto function. Then each B element of B is the image, of course. Each B element of B is the image of the unique element in A. Thus, or we're going to say B. Okay, the image unique element of A, or say B. So then, if f of A is equal to B, thus A is equal to B. And of course, hence, if we're going to look at it, A is equal to B already. So, f of B is equal to B. This will be the thing that we're going to prove, and we're going to seek for. So, now we have, okay, so I will erase this one so that we can proceed with that. So, now, let G denote the mapping. Okay, so from B to A. It should be inverse. Function should be invertible if f from A to B is equal to the function from B to A. So it is invertible now. So we have, or this can be defined as by G of B is equal to B. Okay, we will do the mapping now. First one, you have composite of this of A is equal to G of F of A. That is equal to G of B, and that is equal to B equals to A for every element, or for every A element of A. So we have another one. We have F O G of B is equal to F of G of B, that is equal to F of B, which is equal to B for every element of B. Hence, G OF is equal to 1 sub A, the identity function. So therefore, accordingly, we have F has an inverse. Okay? Its inverse is the mapping G. So that's all for this afternoon.